this video, we're going to talk about equilibrium. You can think of equilibrium as the extent of the chemical reaction. Now, chemical equilibrium, or just equilibrium, is where you have a reaction that can happen in both directions. So it can happen in the forward direction where the reactants form the products, but it can also happen in the reverse reaction where the products form the reactants. So what the way we represent that is with this double arrow, which shows that the reaction can happen in both directions. Now, the energy required for a reaction to take place is the activation energy. The activation energy for the forward direction is much lower than that of the activation energy for the reverse reaction, as shown in this diagram here. Dynamic equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. That is when we see no change in concentration of any of the species within your equilibrium system. So if you look at it in terms of the reaction rate, the reactants are going to start off decreasing very quickly, and then they're going to even out. While the products are going to start out being formed and making them very quickly, and then it evens out. When the rates become equal, that is when you have established that dynamic equilibrium. If you look at it in terms of concentration, the concentration of the reactants start out high and they're going to decrease very rapidly, and then they're going to even out. Whereas the concentration of the reactants start out at zero, and then the concentration is going to increase until it evens out. When they do not change anymore, then you have established dynamic equilibrium. What I want you to notice, though, is that the concentration of the reactants is not equal to the concentration of the products. That's not going to happen. They can be very different. However, the rate of the forward reaction is going to be equal to the rate of the reverse reaction at a dynamic equilibrium. If we look at it in terms of this diagram over here, my reactants are light blue and dark blue, and my products are dark green and light green. So before we start the reaction, we only have reactants in solution. So my concentration of my reactants is very high. The forward reaction is going to happen very quickly because I don't have any products yet, so I can't form anything in the reverse process. So I don't have if I don't have any product, then the concentration of my products is going to be zero, and the reverse reaction cannot. Once the reaction has been going for a little bit, I now see that I have some products starting to show up. So my reactant concentration is going to be decreasing. My forward reaction rate is also going to be decreasing. That means that my product concentration is increasing and my reverse rate of reaction is also increasing until finally we don't see any more change. So the reactant and product concentration is going to remain level, not equal, level. The product or the forward and the reverse reaction is going to be constant. Again, remember, the concentration of your reactants is not going to be equal to the concentration of your products. What is equal is the reverse rate and the forward rate of reaction. We can use a catalyst to lower the activation energy. And in doing so, it's going to speed up the reaction. It speeds up that rate of reaction where it speeds up the reaction rate. And in doing so, it not only speeds up the forward reaction, notice that my activation energy for the forward reaction decreases by quite a bit, but so does the activation of my reverse reaction. Activation energy of my reverse reaction is also lowered. So what this means is that the equilibrium is going to be reached faster. Now, which is given the symbol K, capital K, is X over the reactance. And generally, we talk about it in terms of concentration. So let's look at an example. If we just look at a generic reaction where we have A plus B in equilibrium with C plus D, where the lowercase letters represent the coefficients and the uppercase letters represent the molecules. A is going to be equal to the concentration of C raised to the lowercase c times the concentration of D raised to the lowercase d. And we're going to divide that by the concentration of the reactants. So we'll have the concentration of A raised to the lowercase a times the concentration of B raised to the lowercase b. So this is our equilibrium constant, and this is how we can figure it out. In a reaction, the concentrations can vary. You can manipulate the concentration between different reactions. However, that ratio is going to remain constant. Initially, it might not be that, but as soon as equilibrium is established, the forward rate is equal to the reverse rate, then you're going to have that K and it will remain constant. So let's talk about what K means. Now, when K is really, really big, so it's much greater than 1, the only way we can get a really big number is if the number on top is much bigger than the number on the bottom. And remember, the number on top is talking about the products. So K is much bigger than 1, means that there has to be a lot more products in the equilibrium. So this means the equilibrium is going to favor the product. Now, if K is much less than 1, has to be much bigger than the number on the top. So that means we have a lot more reactants in our equilibrium system. So in this case, the equilibrium system is going to be favoring the reactants. If you have a really big K, then your equilibrium system favors the products. If you have a really small K, then your equilibrium system is going to favor the reactants. When K is equal to around 1, then that's when we have a dynamic equilibrium. And we say that when K is about equal to 1, we have a dynamic equilibrium, but really it's when K is greater than anything times 10 to the negative 3 and less than anything times 10 to the 3. That's generally when we're going to have a dynamic equilibrium. Let's get some practice with writing out or equilibrium expressions. So an equilibrium expression is when your A equals. do your products over reactants. In the formation of ammonia, we have ammonia on top. So it's going to be the concentration of ammonia squared over the concentration of nitrogen times the concentration of hydrogen cubed. So this is the equilibrium expression for this equilibrium system. The equilibrium system of nitrogen gas reacting with hydrogen gas to yield ammonia. But then ammonia turns around and decomposes into nitrogen and hydrogen gas. In our second example, I want you to look at the states. In our first example, all of the states were the same, so we had a homogeneous equilibrium. In our second example, not all of the states are the same, so we have a heterogeneous equilibrium. Now, when we write out our equilibrium expression, K equals and its products over reactants, we look at it in terms of concentration. I can have the concentration of CO times the concentration of H2 divided by, I want you to think about this. Can a solid have a concentration? Remember, when we're talking about concentration, we're usually talking about how much solute is in the solution. Well, if I just have a solid, I don't have two substances, so I can't have a solution, which means I can't have a concentration. So that means I cannot include the solid in my equilibrium expression, and I will just include the water vapor. So this is very important. Solids and liquids are not included in the expression is because they don't have concentration. So in this next example, I have another heterogeneous equilibrium because the states are not all the same. When I write my equilibrium expression, I cannot include any solids or liquids. So in this case, I'm going to have the concentration of hydronium ion cubed times the concentration of phosphate divided by the concentration of phosphorus. Notice I did not include water because in this case it is liquid. In the previous example, I did include H2O, but that's because it was water vapor. In my next example, it is liquid water, which does not have concentration.